Alright, hey guys, welcome back to another video. Today we're going to start chapter 3, which is called Combinatorial Principles, and we'll start on section 3.1, Permutations and Combinations. And okay, so we'll go over what permutations and combinations are and how we can, well, we'll see. Well, I'll go over this. But the first thing I want to show you guys is what is known as n factorial. So n factorial is written as n with an exclamation mark. And it's that exclamation mark right there that gives it the name of factorial. Now, what this looks like written out is n factorial is equal to n times n minus 1 times n minus 2, and we go all the way until we get times 3 times 2 times 1. Okay, so I'll use like an actual number as an example. So let's look at 4 factorial. If we write 4 factorial out the way it's written here, the first thing we would write is the n, which is 4. 4 times n minus 1, so 4 minus 1 is 3, times 3, times n minus 2, 4 minus 2 is 2, times 1. And this is equal to 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So this is what factorial is in like the general form, and this is us using a specific number as an example. So you're basically multiplying the number times every number that comes after it together. So if we had a bigger number, 12 factorial, then it would be 12 times 11 times 10 times 9 times 8, all the way until we get to times 1. And this will be useful for what we're going to look at here in a second. Okay, so the first thing we'll look at are permutations. So what are permutations? So the definition it gives us is that it is the number of different ways we can order or permute n amount of objects, which is n factorial. Okay, so if we have, if we have 4 different things, it's how many different ways we can order those 4 different things around. And that would be the same as the factorial. So if we have 4 objects, that means that there are 24 different ways we can put them in a different order. Now, if we're choosing an ordered subset of size k, without replacement from a collection of n objects, the number of ways of doing this is n factorial over n minus k factorial. Okay, now without replacement, I mentioned without replacement, that's very important, and you'll see here in a second why. So, okay, like for example, if we have a subset of 2 items, right? Or hold on, if we're choosing a subset of 2 items from a total number of 3 items. Okay, so yeah, let's say we have, let me write this more to the side. N minus k factorial. Okay, so I'm gonna erase that. So just as an example, let's say we have the subset 1, 2, and 3. Now, we're asked to take 2 of these elements from this subset of 3, and we can order them in, let me go back. So we're choosing a subset of 2 items from a total number of 3 items, then the total number of ways of choosing an ordered subset of 2 is this right here. Okay, so what does that look like? So we have a total of n equals 3 items, and we're looking at a subset of 2. Now, if we're using this formula right here to give us an answer, it would be equal to 3 factorial over 3 minus 2 factorial, which is 6. Okay, now that's easy, right? Like, we can just take any number and put them into an equation, but what does this actually look like, I guess, drawn out? Well, let's take how many possible subsets of 2 from a total set of 3 can we make, is what this is asking. So, we have the elements 1, 2, and 3. That means we can make the subset 1 and 2. We can make the subset 1 and 3. We can make the subset 2 and 3. We can make the subset 3 and 1. We can make the subset 3 and 2. And we can make the subset, let's see, 1, 2, 1, 3, 2, 3, 3, 1, 3, 2, and 2, 1. That's right. Okay. This is what we're talking about here. We have a total set of 3, and we're trying to see how many possible 2 subsets we can make from 3 elements, which is all of these right here. And you'll notice also that, like, for example, 1, 2, and 2 and 1, they have the same elements, the 1 and the 2, but they're in a different order. So here we have 1 first followed by 2, here we have 2 first followed by 1, but they don't count as the same subset, they're still different. Just because they have the same elements, but they're in a different order, that is a different permutation. So that is why the total possible of 2 subsets we can make, or the total possible amount of subsets containing 2 elements is 6. And I just wrote them out right here. And okay, likewise, if we have a total set of 4 elements and we were asked to make all the possible, well, here I can just, draw this out as well. This one's going to take a little longer, but okay, so we understand where the 6 came from. All right, now let's include a 4th element. So let's say we have 4. How many possible 3 element subsets can we make? That would be equal to 4 factorial over 4 minus 3 factorial. So 4 factorial is 24. 4 minus 3 is 1. 1 factorial is just 1. So that is equal to 24. Okay? So there are 24 possible 3 element subsets we can make. And I'm going to try to draw all of them out. 1, 2, 3. 1, 2, 4. 1, 3, 4. 1, 3, 2. 1, 4, 2. Let's see. 1, 2, 3. 1, 2, 4. 1, 3, 4. 1, 3, 2. 1, 4, 2. 1, 4, 3. 1, 4, 3. Alright, so it looks like I got all the ones that start with 1. Now we'll do the ones that start with 2. So 2, 3, 4. 2, 1, 3. 2, 1, 4. 2, 4, 3. 2, 4, 1. 2, 3, 1. Yeah. Let's see. 3, 4, and 4, 3. 1, 3, and 3, 1. 1, 1, 4, and 4, 1. Okay, now what about the ones that start with 3? 3, 1, 2, and 3, 2, 1. 3, 1, 4, and 3, 4, 1. And 3, 2, 4, and 3, 4, 2. Alright, now the ones that start with 4. 4, 1, 2, 4, 2, 1, 4, 1, 3, 4, 3, 1, 4, 2, 3, and 4, 3, 2. Okay. So starting from here down, these are all the possible subsets containing 3 elements from a 4-element set. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 6, 12, 18, 24. 24. And like I said, this is what this represents. If we're given a total number of elements in a set and we're asked to find how many possible subsets of a given number we want to find, we use this formula. So if we're asked to find all the possible 3-element subsets from a total set of 4, then there are 24 total subsets, which I wrote them all out right here. So that's what that means. Okay. Now, and also this is also given, like, this is the formula we would use if all of the elements in the set are different, right? We have 1, 2, 3, 4. Those are 4 different elements. But what if we have elements that are the same? Okay, so I'll erase this. Alright, if we have objects that are objectively the same type of object, then the way to order these objects is like this. So n factorial, which is again the total number of elements in the set, and then we have n1 factorial times n2 factorial times, and we go all the way until we reach nt factorial. Okay. Again, this is the total number of elements in a set. This n sub 1 represents one type of element. N sub 2 represents another type of element until we get to the final type of element. And you'll notice that they all have the exclamation mark after them, so we have to do the factorial for these as well. Okay, now as an example, to better illustrate this, let's say we have a set that has A, B, B, and C. Okay? So we have 2 A's here. So we'll call the A's, we'll call them type 1. We have 2 B's here. So we'll call these type 2. And we have a C, and that'll just be our type 3 because it's different, right? So we have 3 types of elements. Now, if we want to find the total number of ways to order these objects, excuse me, you know, like, just like, yeah, like in a different order, like so A, B, B, C, that's one order, but we could also do A, B, C, B, that's a different order. A, B, C, that's a third order. If we just want to find every possible way to rearrange these 5 elements, then we would use this formula right here. So again, the total number of elements is 5 over how many are in the first type of, how many elements are in type 1? There's 2, so that's 2 factorial, times how many elements are in type 2? There's also 2. 2 factorial times 2 factorial times how many elements are in type 3? There's just the 1c, so there's 1 times 1 factorial. That is equal to 30. That means there are 30 possible ways of rearranging these 5 elements so that they are in a different arrangement, basically. Right? And also, we're not counting these 2 A's as the same. They're different A's, they're different elements. They just look the same, but they're not the same thing. So like, yeah, if we wanted to be like even more specific, let's say that we have A sub 1 and A sub 2. So A sub 1, A sub 2, BBC, that's 1, but then we could just flip these A's so that they, you know, this A goes here, this A goes there. A sub 2, A sub 1, BBC, that's another, that's still different. So again, there are 30 possible ways of rearranging these 5 elements. Okay. Next, we'll look at combinations. Okay. So this was permutations, what we just went over. Now we're going to look at combinations. And they're almost the same thing, except in permutations, we look at elements without replacement, right? So that's what I said, yeah? Yeah, so like, but here for combinations, we're looking at elements, we're looking at subsets without replacement and without regard to the order. So let me read the definition here. Given n distinct objects, the number of ways of choosing a subset of size k without replacement and without regard to the order in which the objects are chosen is, and this is the formula for combinations, it's n factorial over k factorial times n minus k factorial. Okay. And this is where the phrase n choose k comes from, right? So like, that just looks like this. It's like n c k. Or is it a p? No, it is a c. Or it looks like this. It's like they're both in parentheses like that. Okay, so this is for combinations. Now, to further illustrate this formula right here, we'll look at an example. So, okay, let's say we have a set of 3 elements, A, B, and C. If we choose a subset of 2, right, like the possible subsets of 2, then we would use this formula. So we have 3 elements, right? So that's n is equal to 3, and we want to create all the possible subsets of 2. K is equal to 2. Then this is 3 factorial over 2 factorial times 3 minus 2 factorial. So 3 factorial is 6, 2 factorial is 2 times 1, so that's just 3. So, and these are easy to write out. What are all the possible subsets of 2 elements from this set right here? Well, that would be A and B, A and C, and B and C. And that's it. Now, in permutations, what we looked at, you remember me talking about, well, you know, like these 2 A's are the same, so like it doesn't matter which order they go in, they're still different permutations. Here, the order and the elements that are in each subset does matter. And what I mean by that is, the reason it's 3 is because you can't say that this subset A and B and the subset B and A, these are the same thing. These do not count for 2 separate things, for 2 different subsets. AB and BA are the same. That's why there aren't 6, right? There's just 3. So, but in permutations, these would be counted separately, right? A, B, and BA, those would be separate permutations, but for combinations, they're not counted separately. They are the same combination. Just because they're in reverse order, but that doesn't mean that they're different. Okay. I'll just do another quick example showcasing this equation right here. Let's say we have a set of 4, right? We have A, B, C, and D. And we wanted to find all the possible subsets of 2, so k is equal to 2. So 4 factorial over 2 factorial times 4 minus 2 factorial. Well, that's 24. 2 factorial is 2. 4 minus 2 is 2. 2 factorial is still 2. 24 divided by 4 is 6. And I'll show all of the 2 element subsets here, which is AB, AC, AD, BC, BD, and CD. And that's it, right? And again, CD and DC would be the same thing, so they're counted as 1, not 2. And that's all of the 6 possible 2-element subsets from a 4-element set. Okay. Now the next thing we'll look at is let's see how I want to. Well, here, I guess, yeah, we'll look at the binomial theorem next. Let's write it here. Binomial theorem. This is an important theorem for like series and like Calc 2, but it's also good to look at to see like how we get coefficients in a binomial equation, I guess. Okay, so the definition says, in the power series expansion of 1 plus t raised to the n, the coefficient of t to the k is n choose k. Okay, so if we were to expand 1 plus t raised to the n, this would be equal to the sum of the elements k that go from 0 to n of n choose k times t to the k, and this written out is equal to 1 plus nt plus n times n minus 1 over 2 plus, got t squared there, n times n minus 1 times n minus 2 times t cubed over 6 plus blah blah. Okay. Literally, what does any of this mean? I'll show you. In an example, let's say we're given the equation of x plus y raised to the 4th. Okay, if we were to write this out, if we were to expand this, it's going to look like this. It's going to be x to the fourth plus 4x cubed times y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Okay. Now, what the binomial theorem tells us, or what it helps us with here, is basically finding the coefficients of the elements here. Okay, this is where a calculator really comes in handy, because you don't want to have to write out all of the combination, you know, like n factorial over. That's basically what this is doing here, right? This is like the combination equation in front of our variable. In this case, it'd be the x and the y's. Sorry. But like, you don't want to have to write all of this stuff out to try and see where all of these coefficients came from. So I'm going to use a calculator. Okay. Now, basically what this is saying is, if we wanted to include the binomial theorem in this answer right here, it would look something like this. So the coefficient here in front of the x to the over 4 is understood, it's an understood 1. And they got that 1 because we're basically doing a 4 choose 0 in front of the x to the 4th. And if I put it here in my calculator, where is it? It's the one that says PRB, probability, and there's one that says NCR, hit enter. If I do 4 choose 0, I'm getting a 1. I don't know if you guys can see that. So that's how this 1 showed up there. Same thing with this 4. This is basically a 4 choose 1 x cubed y. 4 choose 1 is 4. Same thing with this 6. Oh, and we actually showed this earlier, right? We showed it with the set of 4 and all of the possible 2-element subsets. There were 6 total. So that is a 4 choose 2 right there. X squared, y squared. This 4 comes from 4 choose 3, x, y cubed. And there's another 1 right here, and that's just from 4 choose 4. Y to the 4th. I ran out of space. So this is the way we'll use the binomial theorem in this section. Basically, in every binomial theorem, or in the binomial theorem, we're doing a combination equation for the coefficients. So again, that 1 that's in front of this x to the 4th, is a 4 choose 0. This 4 is 4 choose 1, this 6 is 4 choose 2, this 4 is 4 choose 3, and that 1 is 4 choose 4. And, I mean, look, if we'd written like a 5 here, then it would be, you know, x plus y to the 5th. We'd write out the whole equation like we did here. Same thing, those coefficients, that would be a 5 choose 0, 5 choose 1, 5 choose 2. So in total there are 1, 2, 3, 4, 5. There are n plus 1, you know, terms that get, like, you know, you multiply the thing out, you get n plus 1 terms. So here, because it was to the 4th, 1, 2, 3, 4, there are 5 terms. If it were 5, if it were raised to the 5th, there would be 6 terms, so on. But this is not exactly using like the binomial theorem to its fullest extent, but it's just showing us again how these coefficients come to be in relation to the combination equation that we just did earlier. And again, that's where the coefficients come from. Okay. Now, what about, there's another theorem. There's a second theorem. It's called the multinomial theorem. And it's kind of the same thing. So this says, in the power series expansion of this, okay, let's see. Okay, this actually goes back to the types. So this involves the types, like different types of elements. So let me see if I can kind of simplify or like try to make it more understandable. Well, okay, here, maybe I'll just write it out and start to explain. Okay, so in the power series expansion, so let's say we have, and this is like the general form of that x plus y to the fourth. But let's say we have something that looks like t1 plus t2 plus all the way to ts raised to the n, and n is a positive integer. Then the coefficient of, any one of the terms will be equal to n factorial over k sub 1 factorial plus, times k sub 2 factorial times, all the way to k sub s, I'm using k sub s factorial. Okay. So you'll notice this looks, again, like I said, like that x plus y to the fourth. And if we want to find the coefficient of any one of those terms, we're basically going to use this formula right here. Okay, now I'm going to use this in an example. Okay, now suppose we have this equation. We have 1 plus x plus y, all raised to the fourth. Now, what does this look like in the expanded form? Let's, we multiply all of these terms out. What does it look like? It's really long. It looks like this. X to the fourth plus 4x cubed y plus 4x cubed plus 6x squared y squared plus 12x squared y plus 6x squared plus 4xy cubed plus, I'm going to keep going down here, 12xy squared plus 12xy plus x plus y to the fourth plus 4y cubed plus 6y squared plus 4y plus 1. All right. Again, we have this equation. We multiplied everything out, or I guess in this case we raised everything to the fourth, and this entire 2 lines of work is what it is. Okay. The capital N, again, is the coefficient. So in this case, n is equal to 4. N is equal to 4. Now let's say we want to find the coefficient of the term xy squared. If we look through here, we have right here that the coefficient is already 12. But using this multinomial theorem, using this thing right here, how can we for sure, how can we be sure that it's 12? So in this case, we have okay. Okay, so let me backtrack. Let's say, again, we want to find the coefficient of x, y squared, right? Now, what might not be so easily easy to see is that since we're just looking at the variables x and y here, and we're trying to find that coefficient, or we're trying to make sure that it is 12, for now there's like an understood 1 right here. So now we have three different types of elements, right? We have the 1, we have the x, and we have the y. Well, actually, we have 2 y's, according to this, because it's y squared. Okay, and each of these will be each one of these k's that we have in the general form of the multinomial theorem. So k1 is equal to 1 because there's only one 1. K2 is equal to 1 because there's only one x. And K3 is equal to 2 because the y is being squared. Okay. Now, we can basically use that n choose k equation here, or I mean, we're going to use this basically, in order to find that coefficient that belongs in front of this xy squared. So again, we have 4 factorial, n is equal to 4, 1 factorial, k1 is equal to 1 factorial, times k2 is equal to 1, k2, so that's another 1 factorial, k3 is equal to 2, so that's times 2 factorial, and that is equal to 12. And look, that is exactly what the coefficient is in front of the xy squared. Okay, now let's maybe do let's choose any other one. Let's do, I guess here, we'll use x squared, y squared. So we see that there's a 6 right there, right? But maybe we just want to be sure that, like, oh my god, it really is a 6. So, again, we'll look at x squared, y squared. X squared, y squared. And remember that we got rid of the 6, but there's still an understood 1 there. So k1 is equal to 1, there's 1. K2 is equal to 2, x squared. K3 is equal to 2y squared. Our capital N is equal to 4, so 4 factorial over 1 factorial times 2 factorial times another 2 factorial. And that is, well, that's 24. 1 times 2 times 2, 2 to 4, that's 4. 24 divided by 4 is 6. And yep, look, we said that there was a 6 there, that's why there's a 6 there. So again, we're illustrating the relationship between the binomial and the multinomial theorems and permutations and combinations. And right, this is just another way of proving that these coefficients in front of these terms are truly what they are. If we went ahead and did the work using this standard form of the multinomial theorem or of the, then we can prove that, oh my god, that really is that coefficient because we solved it over here. Okay, there's one more thing I'll go over in this video, and that is just an example highlighting more or less the combinations, right? In a real world example. Okay. And honestly, this is kind of easy. So let's say we have a purse, and it has one of each coin, right? So we have a quarter, a dime, a nickel, and a penny. Then how many possible ways can we choose 2 coins? Well, if we have 4 total coins, and we're asked how many ways we can choose 2, 4 choose 2, that's equal to 6. And again, that comes from 4 factorial over, and I already forgot how it went, from the combination equation. Okay, 2 factorial times 4 minus 2 factorial. So that is 24 4 minus 2 is 2, 2 factorial is 2, 2 times 2 is 4, and that's 6. And this is what you would put in your calculator if you wanted to find that also. This is just like the written out form. And yes. Okay. And remember, it's only 6 because, like, if we pulled out a quarter and a penny, shuffled them in again, and then pulled out a penny and the quarter, that's still the same. That's the same combination. It doesn't matter which one comes out first or which one comes out second. If it's the same 2 coins, then it's the same combination. So that's why it's 6. Okay, so now it's asking us, what's the probability that one of the coins is either a quarter or a dime? Well, let's write out these 6 different combinations out. Let's just write them out. So we have, capital letters, quarter and dime, quarter nickel, quarter penny, dime nickel, dime penny, and nickel penny. Okay, so these are, again, the 6 possible different ways that we can pull out 2 coins from a purse that has 1 of each coin. And it's asking us, what is the probability that one of the coins is either a quarter or a dime? So we look at all of the combinations that have either a quarter or a dime. So this one has both, okay. So that one, this one has a quarter right there, that one has a quarter right there, this one has a dime right there, this one has a dime right there, and that one doesn't have either of them. So the probability is 5/6 because 5 of the combinations have either a quarter or a dime. And so the probability that we pull out either a quarter or a dime from any of the subsets that have 2 coins is 5/6. So yeah. And there are like 8 problems to go over, but I'm going to end the video right here, and then the next video I'm just going to dedicate to the end of chapter problems. And hopefully these, hopefully this makes more sense in terms of like, permutations, combinations, what it means when it's without replacement, what it means when it's without order. So yeah, that's what we'll look at in the next video.